My workshop.
Okay, thank you for coming today. Believe it or not, it's the last day of class before spring break. I think that's right. Not ahead of myself, right? So this will be uh, the last one for a while. I forget how we set up the homeworks, but there's only going to be one of those homework assignments due the next 2 weeks. You don't have one that's officially due during spring break. Um, so just make sure you're updated on those deadlines, but there won't you will get a break from homework as well. All right. So as you recall, last time we started talking about aqueous solutions. So these are uh, homogeneous mixtures where you dissolve something in water, and we covered how that happened in terms of the polar water molecules separating ions if it's ionic compound or surrounding molecules if it's molecular covalent compound. And we also talked a little bit about the properties of those solutions being strong, weak, or moderate strong electrolytes, weak electrolytes, or non-electrolytes. What we're going to start with today is um, a little bit of a quantitative look at how we define solutions. We're going to come back to a lot of these topics later on when we do stoichiometry at the end of this chapter, but we want to introduce this topic now just because it occurs early and it's something that's important to understand. So when we dissolve something in water, um, just like we did in all of chapter 5, we can, if we have the mass of that substance that we dissolve, we can um, calculate the moles of it. Now, the one thing to be aware of, though, is when you dissolve either an ionic compound or a strong acid in water, as we already talked about in the context of electrolytes, it breaks up into the individual ions. And so if you're asking a question like this, how many moles of ions are present when we dissolve something in water, you do have to think a little bit more carefully about what's happening when you dissolve that substance. So if we're dissolving silver nitrate in water, the way that we can kind of indicate this is that initially silver nitrate is a solid. It looks not too dissimilar from sodium chloride. The picture here is what shows that. And then when we add it to water, there's different ways of indicating this, but you can just put a reaction arrow with water over it, indicating that we're putting that into water. And then what the solution is going to have after that substance is dissolved, again, it's going to look just like a colorless liquid. You're not going to really see anything, but what you would have in the solution is going to be the two ions separated. So silver nitrate is made up of silver plus, which is the cation, and then NO3 minus, which is the anion. And we can write it in this way, where we separate the two ions, indicate that they're both aqueous because they're both dissolved in water. Now, what that means from the standpoint of this problem is that if we dissolve 1 mole of silver nitrate in water, we're going to produce 2 moles of ions. 1 mole of positive ions, 1 mole of negative ions, a total of 2 moles of ions, which is what this question is getting at here. So we're looking for the total moles of ions in this case. So we start with the mass of silver nitrate that we dissolve. That's what's given to us. My tablet's going to crap out early today, so to reset already. I should have probably restarted before. All right, those of you following along on Teams, I will be back in a minute. Let me stop recording so we don't have a big gap either. Okay, I think we're back. All right, we're ready to go. So where we left off, again, we were talking about doing this conversion where we start with 3 grams of sodium nitrate. And then, just like we've done many, many times in chapter 5, we can convert that into moles. But what we have to recognize is that when we use the molar mass of silver nitrate, which is given, so 1 mole of AgNO3 as a mass of 169.87 grams, that's the molecular weight that's given to us. That gives us the moles of the whole thing, silver nitrate. We're looking here for moles of ions. So this is again where we have to look at the formula of the compound and recognize that when it dissolves in water, it breaks up into the individual ions. So for every mole of AgNO3 that we dissolve, we're getting 2 moles of ions in solution. Again, 1 mole of positive ions in this case, 1 mole of negative ions because it's a 1-to-1 ionic compound. But we have to remember to do this last step here. This is the one that many people would forget. So it's mostly a mass to mole conversion, but we're looking for total moles of ions. So we have to do this last step here and double it because there's going to be 2 moles of ions for every mole of compound we dissolve. So we get 0.0353 moles. So when we dissolve something in water, we have to be cognizant of that possibility. If it's an ionic compound in particular, where it would separate into ions, sometimes that's relevant, sometimes it's not. It really just depends on the situation. But in this problem, we had to take account for that. But what's going to be more relevant for most of this chapter is this new concept of molarity. So in chapter 5, we introduced two relationships involving moles, the moles to mass relationship involving molar mass, and then the Avogadro's number, which tells you how many things are in a mole. And then here, as we go forward for the next few chapters, we're going to keep introducing new relationships that involve moles of substance. And this one, in chapter 6, the big one's going to be molarity. So molarity is a concentration unit. It tells you how concentrated a solution is. Um, so you're probably somewhat familiar with the idea of concentration in your everyday lives. I won't use alcoholic beverages as an example because I don't want to encourage bad behavior. But if you're making sometimes you buy like juice drinks at the store that are concentrated when you first get them. And if you were to drink that, it would be like extremely sweet and strong. And then you have to dilute it to make it less concentrated so that it actually tastes like it's supposed to. So that's what I mean by concentrations, how much stuff is in the solution. In molarity, there's a few different concentration units that we have, and you'll cover more of those in Chem 2. The only one we're going to do in this course is molarity, which is the most common and in many ways the most useful. But molarity is equal to the moles of solute, that's going to be the stuff that's dissolved in the solution, divided by the liters of solution. Now, it's very critical that you pay close attention to this definition for some of the problems we'll do. This denominator here is not the liters of the solvent that you use to dissolve it, it's the liters of the solution that would then result when those two things are combined, which usually is not that different in terms of numerically, but there is a key distinction here. So when you're doing some of the questions on the homework assignments and the tests, pay close attention to that, because if you're trying to make a solution of a certain molarity, you don't just dissolve it in that many liters of water. You would have to make sure that you use enough water to get that many liters of solution to make your denominator correct. Yeah. Well, so usually we'll do a lot of example problems today. Usually the way that you do it is for the it's you have to kind of consider both parts. And for the moles of solute, it's often going to be just a mass to mole conversion like we just did. So you would get the moles of solute in that way. And then you would have to, if you're calculating molarity, you'd have to divide it by the volume of solution. Now, in most cases, the volume of solution would be given to you, but it could be if you have the density of the solution and the mass, you could calculate it that way. So there's different ways, but you would have these two things would kind of be determined separately. They're not that closely related to each other. Um, so, but the key point that I'm making at this point is that this denominator here is how many liters of solution you have, not just the solvent that you use to dissolve it, because sometimes those numbers aren't exactly the same. If you're dissolving something in water, especially if it's a lot of something that you're dissolving, sometimes the volume of the solution will expand or contract a little bit depending on the situation, not be exactly equal to the amount of water that you put in. So it's not always obvious at everyday scale, but if you were to take a huge pile of salt, like sodium chloride, you can dissolve like, I think it's like 36 grams per 100 milliliters of water. It's really solid. You can dissolve a lot of it. So if you were to make a really concentrated solution of sodium chloride, you would notice that the amount of water that you put in is not going to be equal to the volume of the solution that you get, because the ions in the sodium chloride, they take up volume, or sometimes the volume even contracts because of the attractions between the ions of the water. It's hard to predict, but the point is it's not always the same. So keep that in mind, just because that's a common place that people get tripped up. But the math is not too bad for this. The abbreviation that we use for molarity is just capital M. So if we say we have a solution that's 2.0 capital M, which is what we're going to do here, that would be equivalent to 2 moles per liter. So if we dissolve 2 moles of solute in a solution that has a volume of 1.0 liters, we would write this as a 2.0 capital M solution. M means molarity, moles per liter. All right, so that's just the terminology that we use. So the key with molarity now, as we move forward, is that we're going to use it in some cases just to calculate what molarity is. That's what comes from this definition. But also, it is now going to be a new conversion factor that involves moles. Because very often when you're dealing with aqueous solutions, you know the molarity of the solution, and the easiest way to measure it is to measure the volume of that solution. So you have now a relationship between the moles of solute that are in the solution and the volume of the solution, which is how we would then use that going forward when we're doing things like stoichiometry, which is coming at the end of this chapter. So this is going to be a commonly used as a conversion factor. We'll do a couple examples along those lines today. All right, so let's just do one where we have to calculate molarity. This is getting at the question that was just asked about, how do we deal with masses of solutes and things like that. So here we have a solution that's prepared by dissolving 15 grams of sulfuric acid, H2SO4, in enough water to form 200 milliliters of solution. Now, this picture here is not actually sulfuric acid, but this is what happens if you add sulfuric acid to, I believe that's sugar, but if you add sulfuric acid to carbohydrates, it basically just chars it. It's not pretty. Which is why you shouldn't add it to your skin, by the way. But anyway, what we're going to do here is just calculate molarity. So we just need the moles of solute and the liters of solution. Now, neither of those are given directly to us in this case, because we're given the mass of the solute, which is H2SO4, and we're given the volume in milliliters. So we have to do a couple of conversions to get these two numbers that we need. Either order we can do it in, but for moles of H2SO4, it's just the same mass to mole conversion that we've been doing. So we have 15.0 grams of H2SO4. The molar mass is given to us as 98.1, so we're going to divide by that to convert grams into moles. Again, we're dividing, just to remind you, because we want grams to cancel out, and we want moles to be what we get. So that gives us 0.153 moles. So that's how many moles of solute you have, but that's just the numerator when we're calculating the molarity. So we have that in the top. And then what we need to also get is liters of solution, which it's kind of given to you, but it's given to you in the wrong unit here. So we have to do a quick conversion. A lot of this you'll be able to do in your head after you do it enough times, but just to remind you, if we have 200 milliliters of solution, we want to convert that into liters to use the correct unit for our molarity calculation. 1 liter is 1,000 milliliters. Or you could put 10 to the minus 3 on top and 1 on the bottom. Mathematically, it's the same, but either way, you'll get that as 0.200 liters. So that is going to be something you have to commonly do in this part of the course, because liters is a pretty big volume of solution. Usually in a chemistry context, we don't work with liters of solution. We work with milliliters. It's more common. You may have already experienced that if you've done some things in the lab. So if we have 200 milliliters, we have to convert that to liters. It comes out to 0.2 as the unit we need for the denominator here. So 0.153 moles over 0.2 liters, we just divide the two to get a molarity of 0.765. Okay, so that's how we calculate molarity. Again, often would involve using things that we've already learned about relationships between mass and moles, like we did here. And then you just have to make sure you include the volume of the solution in the denominator. I don't know what's pulling up here because I didn't do anything. All right. And then this next problem here, that's the only example we'll have for now. We'll do conversions with molarity later on when we do stoichiometry. But the other topic that's then related to this is what's called dilution. There's a saying that the EPA doesn't like, which is dilution is the solution to pollution, but that's not really what we're talking about here. We're talking about it from a chemistry context of, again, dilution means what we're doing here is we have a solution of a certain molarity, solute dissolved in a solvent, and then what we're going to do is we're going to add pure solvent to that to change the molarity, change the concentration. I guess you could do this in either order, but basically you're mixing a solution of some concentration with its solvent, which then produces a solution of lower concentration. Okay, so here's a little picture that kind of describes how molarity works. So we would start with a solution, and then these little red dots are going to represent the solute particles, whatever the molecules or ions or whatever that are dissolved. And I'm counting these out carefully. All right, so for the standpoint of this argument, there's 10 solute particles in that solution, okay? Now, what you do then is you pour it into pure solvent, or you pour pure solvent into the solution, either order. But you would take this concentrated solution, you'd pour it into here. That's the process of dilution. So when you do that, as you can hopefully tell just by my crude drawing, the volume of the solution gets much bigger because you're adding solvent to it, but the number of solute particles stays the same. So we have 10 solute particles here. We're dumping them all in to make a new solution of a different concentration. Those same 10 solute particles still exist. They don't go away or nothing happens to them. But so now we have the same number of solute molecules or solute ions, whatever the case is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but they're dispersed in a larger volume. So then from a qualitative standpoint, what you have is your initial solution has a higher concentration, a larger molarity in a smaller volume. And then after you dilute it, you're going to have a smaller molarity with a larger volume. So you have the same number of solute particles. You didn't change the number of solutes that you have, but now they're dissolved in a larger volume. So that's the key point about dilution, understanding the quantitative aspects of it especially, is that the moles of solute stay the same before and after dilution. So dilution doesn't create or destroy anything. You're not doing chemistry, you're just changing the concentration of the solution. All right, so that's kind of just a quick overview of what we mean by dilution, or kind of physically what you're doing. But then what's more important for us is the math behind it, which is the dilution equation. So using the definition of molarity, which is moles of solute divided by volume of solution, volume in liters in particular. But then if you just cross multiply and rearrange this equation, molarity times the volume is equal to the moles of solute. And as we just said, during a dilution process, you don't change the number of moles of solute. You have the same amount of solute, just dissolved in a different volume at the end. So what that means is that this moles of solute is constant. Before and after the dilution, as we said. So you're not changing the number of moles. And so what that means then is that this product of molarity times volume is also constant. The product of the molarity times the volume that you start with is equal to the product of the molarity times the volume that you end with, and it's going to be written in this way. M1V1 equals M2V2. Whichever order you define it, but conventionally M1 and V1 would be the molarity and the volume before dilution. M2 and V2 would be the volume after dilution, but the product of those has to be constant because you're not changing the moles of solute during this process. So it's a pretty simple equation. And what it also shows, if you think about this, is that if we're using this dilution equation, the volume doesn't have to be in liters. It's not wrong if it is, but because the volume appears on both sides, as long as the units are the same on both sides, the relationship will work. So if you want to keep it in milliliters, that's fine, as long as both volumes are in milliliters, okay? But that's the equation we need to use for any problem that deals with dilution. You know, what are some key words associated with dilution problems? Because the problem won't always have the word dilution in it, but it would be stuff like this. We have what volume of 6 molar NaOH is needed to prepare 250 milliliters of a 0.5 molar NaOH solution. So the key words that tell us that it's dilution. First of all, it's just a single substance. We are going to do stoichiometry later on where we're talking about reactions between two substances in solution, but here it's just NaOH at some concentration, changing to NaOH at some different concentration. So if that's what's happening, if it's just a single substance with the molarity changing, then you should immediately think of dilution. And then that means we need this equation here, M1V1 equals M2V2, and we're typically just going to have 3 of these either provided to us or accessible from the problem, and we solve for the 4th variable, whatever that would be. So we're looking for what volume, so that's our unknown here. We'll call that V1. This is the molarity that's associated with that, M1. So that's M1 and V1, and we're preparing a solution that's 250 milliliters. So that's after dilution, so that's V2, and 0.500 molar is going to be M2. All right, so again, typical problem like this, you have 3 of the 4 things already. You just need to solve for the 4th one. That's your unknown. So we're solving here for V1 as we've labeled it. So that's just going to be M2V2 divided by M1. So then putting those numbers in, what we have is M2, as we said, is the dilute concentration of 0.500 molar. V2 is the final volume, 250 milliliters. As we said, it doesn't have to be in liters. We didn't specify the volume here, what units you should use, but it can be in any unit as long as you're consistent. And then M1 in the denominator, which is the initial molarity of 6 molar. All right, so molarity cancels out, and that means we're going to get an answer for V1 that's in milliliters. So again, pay close attention to your units. That never goes away. But if we do it in this way, we'll get a volume that's directly in milliliters of 20.8. So we would take 20.8 milliliters of the concentrated solution, change the volume to 250 milliliters by adding water, and the new concentration will be 0.5 molar. Are so many questions on that? And mathematically, things aren't too bad with dilution. You just have to keep track of M1, V1, M2, V2, not mix them up. All right. We'll do a slightly more complicated one. No, we're not. Sorry, I cut some practice problems out because I need to save some time today. So that's all I'm going to cover for dilution. There might be some variations on that, but again, it's really just this one equation and figuring out what your unknown is. So, you know, do the homework assignments carefully to make sure you see all the different possibilities, but they won't be much more difficult than this, if at all. All right, so any questions on molarity or dilution? Now, the real sort of, I guess, meat and potatoes part of chapter 6, which is what we're going to start covering now over this lecture, the next lecture, and possibly even a little bit after that if we don't get it all done, is different types of chemical reactions that can happen in aqueous solutions. So we can classify them, we can talk about different aspects of them, and we can see later on then how the stoichiometry for those would work as well. So we're going to talk about a few different classes of aqueous chemical reactions. Let me again orient it here. All right, so the first one is going to be what's called a precipitation reaction. So it's going to be, as we said, 3 categories of reactions to work through, and the first of those is precipitation. Now, when I define this reaction, it's going to sound like kind of like dumb, like what's the point of this reaction? But it is actually fairly important in a lot of aspects with like water purification and transporting fluids over large distances, things like that. And so what happens in a precipitation reaction, it is important, is the bottom line, if you don't believe me. But anyway, what we're doing in precipitation is we're combining 2 aqueous solutions. And normally the 2 solutions we combine each have an ionic compound dissolved in them. And then what happens when we combine them is one, or sometimes more than one, but usually for our purposes just one, insoluble products forms. So initially everything is dissolved in the two individual solutions, but then when we combine them, it produces something that is no longer soluble and that will then fall out of the solution. So testing your memory from the I think it was probably the first or second day of class, the very first video I showed you up here, when I occasionally show those, there was a conservation of mass video. You can go back and look at it again. It's in the notes from that day. There's a conservation of mass video where we had a test tube inside of a beaker, both of them clear liquids. And then when they allowed them to mix together, it formed this like cloudy yellow stuff. And that was a precipitation reaction. So that's taking two solutions, each of them a homogeneous solution where everything is dissolved, but then when you mix them together, something forms that no longer is able to be dissolved, and it just falls out of the solution and as a powder, or as makes the solution cloudy, whatever the case is. Okay, so so here's sort of the way that we determine if a precipitate will form. So when something falls out of solution, we call that a precipitate. So you're either part of the solution or you're part of the precipitate. It's a twist on an old saying. But anyway, what you do first is you consider the compounds that are in the initial solution, and they're each going to be made up typically of their typical ionic compounds, so they're going to have ions associated with them. So we would separate the reactants into their constituent ions. Again, the two initial solutions we're mixing together are almost always going to be just two ionic compounds. You can have precipitation occur also in other kinds of reactions. It can be part of another type, but by itself, precipitation involves just mixing two ionic compounds together. So we separate the reactants into the ions that they would have. So the reaction that video had from the first or second day of class was this one here. They were taking aqueous potassium iodide and combining it with aqueous lead nitrate. Lead 2 nitrate specifically. So again, both of these compounds are initially dissolved in the water in the solution. So when they're dissolved, again, as we talked about earlier today, they're going to break up into the individual ions that make them up. So when we dissolve potassium iodide in water, we're going to get K plus and I minus. Those are the two ions that make up that compound. And then when we have lead nitrate also dissolved, we're going to get lead 2 plus. And then if we care about stoichiometry, remember that lead nitrate has two nitrates in the formula, NO3 2, so we would get 2 NO3 minus. It's not super important that you have the coefficients all there. If you're just trying to identify what the precipitate is, you just have to know what ions are present, not how many there are necessarily. So then what you typically have occurring is the ions are going to swap with each other. So the cation from the first reactant, which is K plus, is going to pair up with the anion from the second reactant. So that's going to be one of your products. And then the other product is going to be the anion from the first reactant, which is I minus, pairing up with the cation from the second, which is lead 2 plus. You're going to just swap the anions and cations with each other. So what we do is we consider the possible combinations. Usually there are going to be two possible products. So in this case, what you would have, as we said, is the cation from the first, which is K plus, combining from the anion from the second reactant, which is NO3. So you'd make KNO3 as one of your products. K plus NO3 minus would form a 1-to-1 ionic compound. And then the second product would be you have lead 2 plus from the second, which is the cation from the second reactant, combining with I minus, which is the anion from the first. Now, you have to make sure you get the formulas correct, especially if you're writing out the chemical equations for these. So lead 2 plus I minus, the correct formula for that would be PbI2, because you need two I minuses to balance the 2 plus charge on lead. When we do these precipitation reactions, we're not changing the charge of anything. That'll come in play when we talk about redox reactions later on. But for precipitation reactions, it's just two ionic compounds, and the charges of all the ions stay the same. They just swap with each other. So those are the two possible products. And then you have to decide, okay, we get these two products. Are any of these going to be insoluble? And that's where you have to use something that is a longtime favorite of Gen Chem students, solubility rules. All right. And that doesn't mean solubility rules isn't like solubility is awesome. It means you have a set of rules that you're going to use to decide if the compounds are or are not soluble. And you have to kind of internalize those to be able to make this. So we make two different products here. It would be possible that nothing happens. If both of these products are soluble in water, then like everything would just stay in solution and you wouldn't see anything happening. But if one or both of them is insoluble, then you would form precipitation. In this case, just let the cat out of the bag, PBI2 is insoluble. That's the yellow cloudy stuff that you saw in the video, if you remember that far back. So this is our insoluble one. That's going to be the precipitate that forms. But to make that prediction, we have to have a series of rules about the solubility of ionic compounds we have to internalize. So your book just has a laundry list of these in no particular order, as it turns out. So I don't really like the way they organize things. It just looks like, oh, there's a long list of rules I have to memorize. So I tried to sort of break it down and systematize it in a little bit to help you a little bit. And basically, what I've done is kind of given you a set of 4 rules that are kind of in a hierarchy from top to bottom. And what that basically means is you want to look for these obvious ones first, because a lot of the problems you do are going to have one of these obvious cases here from either category A or category B, as I've labeled it. And if that's the situation, then you can immediately understand, okay, this compound is soluble, this compound is insoluble. Those are the ones that are very easy to deal with. So category A are going to be ions that are always soluble. So if you have one of these ions in your ionic compound, whatever else is paired with doesn't matter. If it has one of these ions, the compound will be soluble. It will never form a precipitate in that case. So there's some cations that fall in that category. And most of them are the group 1A cations. That's that first column of the periodic table. So if you have an ionic compound that has one of those cations in it, that would be lithium, sodium, potassium, rubidium, or cesium. If your ionic compound includes that as the cation, it will be soluble. It doesn't matter what the anion is, okay? So those ones are always soluble. And then there's one other that behaves the same way, which is ammonium, NH4+. Okay, so if your ionic compound has that as the cation, one of those is the cation, it will be soluble. You don't have to worry about what the anion is. There's also some anions where this is true as well. If you have one of these anions in the formula, the compound will be soluble regardless of what the cation is. So NO3- is probably the most common one that you'll see in a lot of these problems. We just saw it in the example I gave. Perchlorate, ClO4-, acetate, which is CH3COO-, or sometimes written as C2H3O2-. They're written in different ways, but that's just acetate anion. Nitrate is the most common of these. So if you have one of these anions in your formula, regardless of what the cation is that is paired with, it will be soluble. So we saw lead nitrate. The previous example was an example of a soluble ionic compound. Now, category B is going to be the cations and anions where the products that would form are going to be insoluble unless they're paired with one of those special ions from above. So that's why there's sort of a hierarchy to these rules. So the cations that fall in this category, so look for these first because they show up in a lot of solubility problems and they typically are going to be involved in the insoluble product, would be silver Ag+ or lead 2+. So if you have a ionic compound that involves one of these cations, it will always be insoluble unless it's one of these 3 anions up here. So nitrate, again, the most common one. But if it's any other anion that you can think of, you would expect that product to be insoluble. And then there's a few anions that behave the same way, where the ionic compounds that involve these anions will be insoluble unless they have one of these special cations associated with them. So carbonate, CO3 2-, phosphate, PO4 3-, sulfide, S2-, and chromate, CrO4 2-. So ionic compounds with these anions are always insoluble unless the cation is group 1A or ammonium. Okay? So those are the ones you want to look for first because they're obvious. There's no exceptions to those, and they show up a lot. Now, the last 2 rules here are a little bit trickier. So what I'm calling category C here are ions that are usually soluble unless they're paired with one of those cations from category B. So the ones that fall in this category are 3 of the halides. Cl-, Br-, I-. Most ionic compounds with these anions are soluble. Again, unless it has silver or lead, the two cations that are always insoluble. And then there's two other exceptions that aren't as common but might come up from time to time. If you have copper plus, which is related to silver plus, or if you have mercury plus, which exists as a dimer, Hg2 plus, those form insoluble halides. Those don't come up as often, but you do want to be aware of them. But halides are usually soluble unless they have basically one of those four cations: silver plus, lead 2 plus, the two that we already mentioned, or these are two other exceptions that are less common but do come up. All right. And then finally, the last solubility rule, the way that I categorize them, are the ions that are what I call in between annoying ones, where they have, some of them are soluble, some of them are not, depending on what they're paired with. These are there's really two anions that are in this category, and you just have to remember these and be aware of them. So sulfate is one of those. Sulfate is usually soluble. Sulfate salts, I should say. So salts that have sulfate as the anion are usually soluble, except with one of those special cations from category B, which is almost always insoluble, so don't forget about those. But they have a few other exceptions as well. Now, it turns out one thing that's nice about these two in between and annoying ones is that the exceptions are the same for both. They just work in opposite directions. So for sulfate, it's usually soluble, except for category B and except for the last three alkaline earth ions: calcium, strontium, and barium. So that's the second column of the periodic table towards the bottom. Um, those cations paired with sulfate are insoluble, even though most sulfates are soluble. And then OH minus has the same exceptions but works in the opposite way. Compounds with hydroxide are usually insoluble, except if the cation comes from category A. So if it's sodium, lithium, potassium, and so on, those hydroxides are soluble because those compounds are always soluble. So they're usually insoluble, but they have the same exceptions where it just works in the opposite direction. So calcium, strontium, and barium hydroxide are also soluble. So essentially, the only soluble hydroxides for our purposes are going to be either the ones where the cation is always soluble, where you don't even have to think about what the anion is, so lithium, sodium, potassium, and so on, or these three here: calcium, strontium, and barium hydroxide are also soluble. So those ones you have to do a little bit more, require a little bit more thought process to internalize and remember. But look for the obvious ones first, as we said. Look for group 1 cations, because those are always soluble. Look for nitrate, that's always soluble. Look for lead and silver, because that's almost always insoluble, and so on. So look for those obvious ones first, but you do need to kind of know all of them if you really want to fully internalize this. So here's how, just in case you don't have it or wanted to compare more easily, this is the rules from the book. Again, they break it down into 6 rules, and there's not really like a lot of way, it's not very systematic in my opinion, so that's why I did it the way that I did. Okay, so you have to learn those rules to be able to do this part of the course. That's just the reality. But what we also need to talk about then is how do we write the chemical equations for precipitation reactions? So when you have any reaction that happens in aqueous solution, it turns out there's going to be 3 different ways of writing the chemical equation. It's not quite as simple as it was before with more standard chemical reactions. So the one that's probably still the most common and looks the most similar to what we're already familiar with is called either the molecular equation or the formula equation. This is where you just have the full set of reactants and products written as intact ionic compounds. So in other words, we don't separate ions at all when we're talking about the formula equation or the molecular equation. We just write everything as it's paired together. So for the one we've been dealing with in this example here, we had potassium iodide. Now, what is fairly important is to put these little AQs next to the things that are soluble. So anything that's a soluble ionic compound would be dissolved in water and needs to be indicated as AQ for it to be correctly denoted. We combine that with lead nitrate. which nitrates are always soluble, so that one is 2. And then the 2 products. We had KNO3, all potassium salts are soluble, all nitrate salts are soluble, so that's definitely still AQ. And then we formed PbI2. Lead 2 plus is almost always insoluble, which is certainly true with halides. So that's going to be our precipitate. So that gets the little S next to it, indicating that it forms a solid and is no longer dissolved in the solution. That's what the S tells us. Now, usually these aqueous reactions do require coefficients sometimes to balance, and they're usually pretty small, so we can do it sort of by ion. So we have 2 nitrates on the reactant side. NO3 minus appears twice. So we need 2 of those products to balance that. That means we now have 2 K plus and 2 I minuses. So we get a 2 there. So most of the coefficients for aqueous reactions are, 1, 2, 3, very small coefficients, but you need to make sure it's balanced. So that would be the formula equation. Everything is written in this way where we don't separate anything. We write the full formulas of the compounds. For the total ionic equation, we separate any of the ionic compounds that are soluble into their ions. So again, the soluble ionic compounds in an aqueous chemical equation are the ones that have AQ next to them, based on the solubility rules. And we separate those into ions in the total ionic equation. Because as we said, when something is dissolved in water, if it's an ionic compound, it will break up into its individual ions. So for this one here, we would have Ki is aqueous. So when that dissolves, it's going to get 2K plus and 2I minus. I have to write this small because I have to write a lot of stuff to write now. We have lead nitrate. When that dissolves in water, it's aqueous, so we get lead 2 plus AQ and 2NO3 minus, which is AQ. Typically, everything on the left side of the arrow is going to be aqueous, is going to be separated into ions. You're starting with 2 soluble compounds that you're combining together. And then on the right side of the arrow, we still want to separate KNO3 because that's soluble. So that's going to give us 2K plus and 2NO3 minus. We have to keep the coefficients in play here. And then lead iodide, though, is insoluble based on our solubility rules, and it has a little S next to it in the chemical equation. So that one we don't break up because, again, it forms a solid. It's no longer dissolved in the solution. So that one stays as PbI2 solid. And then finally, this total ionic equation is not a very common way of writing things, but it's useful to get us to this last one here, which is sometimes helpful, which is called the net ionic equation. So what we do to produce the net ionic equation is we remove what are called spectator ions. Those are going to be aqueous ions that appear on both sides of the arrow, where essentially there's no net change involving those ions. They're just dissolved in the solution in the reactant side and dissolved in the product side. So there's no net chemical reaction involving those, so we can basically cancel them out. So that's what a net ionic equation does. It removes spectator ions which appear on both sides of the equation. So writing the total ionic equation is sometimes helpful for getting to that, because if we look at our total ionic equation, we see that on the left side we have 2K plus AQ, and on the right side of the arrow we also have 2K plus A2. So K plus is one of our spectator ions. We'll put an X next to it. And then nitrate, NO3 minus, is dissolved over here as an aqueous ion on the left side and also as an aqueous ion on the product side. So NO3 minus AQ appears on both sides. So when we write the net ionic equation, we just remove those 4 ions that are appearing, or those 2 ions, I guess, that are appearing on each side of the arrow. Conventionally, we write it in order of cation plus anion. So the net ionic equation for this would be most commonly written as Pb2 plus AQ, that's on the left side, along with 2 I minuses. And then all that's left on the right side is solid that forms between them, PbI2. So in a precipitation reaction, the net ionic equation is going to include whatever ions, the 2 ions typically that are combining to make the insoluble precipitate that forms. So you have here Pb2 plus, 2 I minuses forming PbI2. K plus and NO3 minus would be spectator ions because they are on both sides of the equation, aqueous the whole time. All right, so any questions on that? All right, so then what we also will move on to is some example questions that use that. So we want to write the molecular, total ionic, and net ionic equation for the reaction that occurs between sodium sulfate and silver 1 nitrate. All right, so there's 3 steps here. So we would have you not do all of these for a homework question, but at least one of these 3 you'd have to do. So again, the molecular equation is typically a good starting point because it just allows us to write out the formulas of the compounds that are involved, predict which ones are soluble and insoluble, and it gives us a lot of information right off the bat. So what we have here for this one, we're not giving you the formulas. Here we're giving you the names. So you have to be able to go from name to formula. So sodium sulfate, sodium is a group 1 cation over there in the first column, and sulfate is SO4 2-. So the formula for that would be Na2SO4. So and that's going to be soluble because all compounds involving sodium would be soluble, and typically everything on the left side of the arrow is anyway. As a reminder, if you didn't feel like you learned nomenclature of ionic compounds very well in chapter 3, or you feel like you've forgotten some of it, it's a good time to refresh that because a lot of problems will be in this format where we give you the names of the compounds that are involved, but not necessarily their formulas. So sodium sulfate is Na2SO4. If you don't realize why that is, make sure you review that or ask me afterwards. And then we're combining that with silver 1 nitrate. So silver 1 nitrate is Ag plus 1, NO3-, so just AgNO3. And then on the right side of the arrow, we just swap the cations and the anions. So sodium, which is our cation from the first reactant, is going to pair with nitrate to make the first product. So it makes sodium nitrate, which is NaNO3. And then silver, which is our cation from the second reactant, Ag plus, is going to pair with sulfate SO4 2- to make the second product. So that would be Ag2SO4. And then we have to predict if either or both of these products is insoluble and mark it with an S. So sodium nitrate has Na plus, which is always soluble, and it has NO3-, which is always soluble. So even if you only remember one of those 2 rules, you should recognize that this is going to be aqueous. But then I'm going to move this over a little bit. For silver sulfate, most silver salts are insoluble unless it's nitrate, perchlorate, or acetate. So this one would be insoluble, and we would mark it as a solid. All right. So you have to make sure you get the formulas of the compounds right, and you have to use your solubility rules to predict which ones will be aqueous versus solids on the product side. So that's our molecular equation. The total ionic equation, which is not by itself very useful, but is a good intermediate to get us to the net ionic, is going to be just taking everything that's aqueous and separating it out. So from sodium sulfate, we have 2 Na plus. There's a little subscript of 2 there that tells us that there's 2 sodium ions in the formula, paired with SO4 2- as the anion. And then AgNO3 is Ag plus, is the cation. NO3-. So you have to remember the charges and the formulas for polyatomics, and this part is going to come up a lot. And then on the product side, we forgot to balance it. I screwed that up. So we have to have a 2 there, and there should be a 2 there as well. Sorry about that. I skipped a step. So our initial reaction wasn't balanced, but it is now with those 2 coefficients. So we have 2 silver pluses and 2 NO3-, and then on the product side, we have 2 Na plus, 2 NO3-. You should have the same number of anions and cations on each side. So if you don't, then check your coefficients or check your formulas. And then we have our Ag2SO4, which is our precipitate, so we don't separate that one. That one's going to stay as Ag2SO4 solid. Only the things that are aqueous get separated and dissolved into their ions. So that's our total ionic equation, and the last step for net ionic, we have to remove spectator ions. So we have 2 sodium pluses on both sides, so those cancel out. We have 2 NO3- on both sides, and it's going to be then silver and sulfate that combine to make our precipitate. So the ionic equation would be 2 Ag plus and SO4 2- to make Ag2SO4. So you can kind of start taking a shortcut a little bit. If we ask you for the net ionic equation for a precipitation reaction, if you identify which of the products is your precipitate, the net ionic would just be the two ions combining to make that product. So we identified silver sulfate as the insoluble product. So that means the net ionic equation would be the cation, which is silver plus, combining with sulfate, SO4 2 minus, to make Ag2SO4, coefficient of 2 to make sure that silver is balanced on both sides. All right, any questions? All right, so that takes care of precipitation reactions. The next major category that we're going to move to for aqueous chemical reactions are going to be acid-base reactions. So we talked a little bit about acids and bases in chapter 3, just about how to name them and how to recognize them. And now we're going to talk about the chemistry that they undergo. So we have to talk about more detail about what an acid and a base are. There's different definitions of these that you might come across as you move forward in chemistry, but for our class, the definition of an acid is going to be a compound that releases H plus when dissolved in water. We talked about in chapter 3, the formulas of acids are going to typically involve one of our common anions paired with H plus that kind of acts as like the cation almost, even though they're technically covalent compounds. So they release H plus when they're dissolved in water. So their formula is before it. All right, so then the formula for an acid is going to look something like this. It's going to have some number of hydrogen atoms in the formula paired with X, which is some anion, either a simple anion from the periodic table like chloride, bromide, iodide, or one of the polyatomic anions like nitrate, perchlorate, and so on. So X is the anion in the formula. And then N is going to be the number of H pluses that you need to balance the anion's charge. So basically, whatever the charge of the anion is. So if it's a 1 minus anion, you would just have one H in the formula. If it's a 2 minus anion like sulfate, you would have two hydrogens in the formula to balance the charge. So it's just how many H pluses you need to balance the charge. So that's what the formula looks like. And then when you dissolve them in water, they release H plus. A base is a compound that releases OH minus in water. So the vast majority of bases that we'll deal with in this course are going to be soluble ionic compounds that have OH minus in the formula. So that's typically going to be, sodium hydroxide or maybe barium, strontium, those bottom ones there. But one of the soluble hydroxide compounds would be typically what we would classify as a base. You dissolve it in water, it's an ionic compound, and the anion that's then dissolved is going to be OH minus. So most bases then are going to be a metal cation with some number of hydroxide anions, where again, N is the charge of the cation, which is how many hydroxides you would need to balance that charge. Most common bases are the group 1A, so the first column of the periodic table, lithium, sodium, potassium, which would be one metal with one hydroxide. But as we said, there's also calcium, strontium, and barium hydroxide are fairly common as well. Those would have two hydroxides in the formula because it's a 2+ metal ion. But that's what acids and bases kind of look like, and that's a little bit about what happens when you dissolve them in water. Now, we also need to then consider the distinction in some cases between strong acids and bases and weak acids and bases. So if a acid or base is classified as strong, that would also mean that it is a strong electrolyte if it's in a solution, and that means it separates completely into its ions when it's dissolved. So they dissociate completely, meaning they completely separate into their ions. And that, of course, would then mean they're classified, as we talked about last time, as a strong electrolyte. For acids, there's no easy way to look at the formula and predict if it's a strong or a weak acid. So you kind of just have to remember that these are the strong acids. We gave them once before. I'll give them here again for completeness. So the strong acids, most common ones are going to be the halide acids, the acid halides as they're called, which would be all of them except for HF. So HCl, HBr, and HI. Those are the three halogen ions paired with H+. All of them except for HF are strong acids. HF is weak. And then some other common ones would be HNO3, nitric acid. Not as common, but still one you should be familiar with is perchloric, HClO4. And then sulfuric acid is also a strong acid. Not too much of an important detail for this course. Sulfuric acid is a strong acid for one of the two H pluses in the formula. So when you dissolve sulfuric acid, one of the H pluses and the rest of the anions separate completely. The other H plus kind of hangs out with the sulfate a little bit, but it's still a strong acid because one of those will dissolve completely in water. All right, so those are the strong acids, and then strong bases are pretty much all going to just be the soluble hydroxide compounds like we talked about, because when you dissolve those compounds in water, because they're soluble, they will completely separate into the ions, and that's what then classifies it as a strong base. So all of the group 1A, lithium, sodium, potassium, rubidium, and cesium hydroxides, those dissolve in water, so they're strong bases. We said the other not as common soluble hydroxides are calcium, strontium, and barium. So these are basically your strong bases. They're all soluble ionic compounds that involve hydroxide as the anion. All right. Now, a weak acid or base is one that does not completely dissociate, which means it's going to produce some H plus and some OH minus in water, but the compound is not going to completely separate into those ions. It's going to just be a partial separation. You'll talk a lot more about weak acids and bases in Chem 2 if and when you take that course. But we do need to know just a little bit about it here. So when you dissolve a weak acid or a base, most of the molecules remain intact. They don't lose their H plus or the OH minus completely, but they will produce some OH plus or some H plus or some OH minus, which is why they're so classified as acids or bases. So the weak acids are basically any other acid that's not listed above as a strong acid. The most common ones are going to be HF, the other of the halogen mineral acids. Phosphoric acid, H3PO4 is a weak acid. And then acetic acid, which can be written as CH3COOH, or anything that ends in COOH would be classified as a weak acid. Okay, so these are the three common ones, even though there are many more than that. The only weak bases we need to be aware of in this course would be NH3 or something that ends in something similar to that, like it has NH2 in the formula. This is not obvious why this is a weak base because it doesn't even have hydroxide in the formula. So how does it produce hydroxide in water? What happens is that when you dissolve NH3 in water, it reacts with the water to form NH4 plus and OH minus. So it produces some OH minus. It's not a complete reaction. Most of it stays as NH3, but a little bit of it's going to react with water to make some OH minus, which is why it would be classified as a weak base. All right, but you don't have to fully internalize that as long as you remember that NH3 is a weak base. All right, so any questions on just the definitions and categorizations of acids and bases? Okay, the more important thing is going to be talking about how they react with each other. And the sort of essential step that occurs in an acid-base reaction. So an acid-base reaction means we mix an acid and a base together. And what happens is that the H plus from the acid and the OH minus from the base are going to recombine with each other. So for every acid-base reaction, or almost every one, unless there's also precipitation involved in the same process, which isn't very common, but the typical net ionic equation for an acid-base reaction is going to just be the H plus from the acid reacting with the OH minus from the base, and they form water, which can still be written as AQ or just L for liquid. It doesn't really matter, but the key point is that H plus and OH minus react to form water. That's the key thing that happens in any acid-base reaction. So there's always going to be spectator ions present because the acid had some anion associated with it and the base had some cation associated with it. So there will be typically spectator ions that you have to have if you're going to balance the full equation. And then the coefficients as well are going to depend on the formulas of the acids and the bases that we're using. But that process, the combination of H plus and OH minus to make water, happens in every acid-base reaction. at least the types of acid-base reactions we'll talk about in this course. All right, so the spectator ions and the coefficients then for the overall equation will depend on what the formulas are for those. So then if you're talking about the overall outcome, the full molecular equation for an acid base is always going to look like this in very general forms. Acid plus base as your reactants. The H plus from the acid and the OH minus from the base combine to form water. So that's one of your two products. And then the other one, you'll typically have spectator ions associated with these that will combine to make an ionic compound. Where the ionic compound that forms is going to have its cation coming from the base. So if it's a metal hydroxide base, the metal cation is going to then be involved in the ionic compound that forms, and the anion will derive from the acid. All right, but that's what every acid-base reaction typically, almost everyone anyway, is going to look like. Acid plus base, water is one of the products, and then you take the ions that are left over and combine them to make an ionic compound as your second product. So if we just work out a few examples of these, what slides do I have here? All right, we just have a couple more slides. We have plenty of time. So if we want to write an acid-base reaction between nitric acid and potassium hydroxide, would you have to get, again, the formulas of those correct? Nitric acid is the acid that derives from NO3 minus, so it's going to be HNO3. NO3 minus is a 1 minus anion, so it just needs one H plus to balance the charge. And that's going to combine with potassium hydroxide. Potassium is K on the periodic table, first column, so it's going to be K plus with one OH minus. So KOH would be the formula of that. All right, so those are the two reactants. To balance out acid-base reactions, we can first start by writing the products. It's going to be water is always one of our two products. And then the other product, as we said, is an ionic compound that involves the leftover ions. So from HNO3, we have the NO3 minus anion nitrate. And then from KOH, we have the K plus potassium cation. And those two are going to then be left over and combined to form an ionic compound on the product side. So it'll be KNO3. All potassium salts are soluble, all nitrate salts are soluble, so that will stay in solution, no precipitation involved with this reaction. So those are reactants and products, and it turns out for this one, we don't need any coefficients. Now, to help you decide if you need coefficients, one thing that's good to look at initially is how many H pluses does your acid have, how many OH minuses does your base have. In this case, our acid has one H plus, our base has one OH minus, so they're going to react in a 1-to-1 ratio, and they're going to make just 1 mole of H2O when they do that. So you don't need any coefficients there. And then for the ions that are left over, 1 NO3 minus, 1 K plus, make 1 KNO3. So no coefficients are needed here to balance this. Most acid-base reactions have coefficients that are pretty small. 1s, 2s, maybe some 3s thrown in there, but not very common to get more than that. All right, then if we have sulfuric acid and potassium hydroxide, this is one where we will need coefficients to balance it. So we have sulfuric is H2SO4, sulfate anion, which is SO4 2 minus with 2 H pluses to balance the charge. And then potassium hydroxide, same base, so it's KOH. The products still follow the same pattern, water as one of them. And then the ions that are left over. So we have K plus from the base, SO4 2 minus from the acid, so that's going to be K2SO4. Soluble because it has potassium as the cation. All potassium salts are soluble. But here we have to do some balancing. And there's different ways of approaching this, but one way I like to look at it is, again, to think about the essential acid-base reaction that's occurring, H plus plus OH minus. Our acid here has 2 H pluses in the formula. It's H2SO4. So if we have 2 H pluses, we also need 2 OH minuses to completely react. So we can put a coefficient of 2 there. If we have 2 H pluses and 2 OH minuses, that forms 2 waters. And then we don't need a coefficient here because everything's already balanced. Two potassiums in that product, 1 sulfate, 1 sulfate. But we do need coefficients of 2 in front of KOH and in front of water to balance this out. So any questions on that? All right, the last one we'll work through today and before I release you for spring break for this course is going to be a slightly different one that involves weak acids. We want to write the net ionic equation for the reaction between acetic acid and barium hydroxide. So acetic acid is one of our common weak acids. There's a few different ways of writing the formula, but one of the common ways is to write it as CH3COOH. Now I'm bringing up acetic acid here also because the other weird thing about acetic acid is it has a bunch of different hydrogens in the formula. Only the hydrogen that's bonded to the oxygen is going to be acidic. So that's the only one that's going to actually form H plus when you dissolve it in water. Okay, so these three hydrogens are just kind of like they're just there, but they don't separate as H plus in water. Only the one from the oxygen is going to be acidic. So you just have one acidic proton in there. We're going to combine that with barium hydroxide. Barium is Ba, kind of low in the periodic table, but it's Ba, which is going to be the second column. So it's going to be a 2 plus cation, Ba 2 plus, and these two OH minuses to balance. And then we form water, and we form an ionic compound. The ionic compound we're going to form is going to be barium 2 plus with acetate, which is 1 minus anion. So however you write it, it's going to be Ba CH3COO2. All acetate compounds are soluble, so that one would be aqueous as well. Now, when we're writing ionic equations involving weak acids, we have to be a little bit careful with how we do that, because when we write out the total ionic equation, if we do it that way, what we have to recognize is that even though acetic acid is dissolved in water, it's indicated as AQ, it is soluble, but it's a weak acid, so that means it doesn't separate completely into its ions when we dissolve it. So when you're writing out ionic equations for acids and bases, only strong acids and strong bases are going to be the ones that you would actually separate into ions. So acetic acid is a weak acid, so we don't want to separate it when we write out the ionic equations. Most of the acetic acid is going to stay intact without breaking apart into ions. So we need a coefficient of 2 to balance that there, coefficient of 2 there as well. Forgot to balance that. So 2H plus is 2OH minuses, makes 2 waters. But now when we write out the total ionic equation, for acetic acid, we don't want to separate it into ions because it's a weak acid. There will be a little bit of dissociation into H plus and acetate, but most of the molecules are going to stay as CH3COH. Whenever you have a weak acid, that's going to be the case. So don't separate out anything that's a weak acid or a weak base. Barium hydroxide is a soluble ionic compound, so that one we can separate out. It has 2 OH minuses in the formula. And then in the product side, water is just a covalent liquid, so we don't separate that into anything. And then barium acetate is a soluble ionic compound. So we're going to have barium 2 plus and CH3COO minus, both of those aqueous and dissolved. So it looks a little bit different now because on the reactant side, we did not separate out both reactants because one of the reactants was a weak acid. It mostly stays as just CH3COH without dissociation. Only a little bit of dissociation occurs with weak acids. So then for our net ionic equation, we just have to remove spectator ions. And in this case, there's only one spectator ion. The only ion that appears on both sides of the arrow is barium 2 plus. All right, OH minus combines to make water, so it only appears on the left side. We don't have any ions from acetic acid. This acetate only appears on the right side as well. So the only spectator ion is barium 2 plus. So the net ionic equation is just going to be whatever's left over. It's going to be 2 acetic acids plus 2 OH minuses, forming 2 waters, and there should be a 2 there as well, 2 acetates. So that's the net ionic. You notice that in our net ionic equation, everything has a coefficient of 2 in front of it. So it is sometimes possible to reduce that down, because if all the coefficients are 2, we can remove them and balance with just coefficients of 1, just reduce to the smallest whole number of coefficients. So occasionally that'll happen when you're putting a net ionic equation together. If you do it in this way, you'll get to an equation that is reducible. In this case, all the coefficients are 2. The simplest and correct way to write it would just be with coefficients of 1. So you want your net ionic equation to have the smallest possible coefficients, even if the species originally carried coefficients in the previous steps. Doesn't really matter what order you write things in, but the coefficients in this case, all being 1, would be the simplest way to write that. Okay, so that's again, the reason I brought that one up. Oh, went away. It'll come back eventually, maybe not in the correct format. It did just go away. All right, write out again. 1-to-1 coefficients is fine for this, but the key thing is you don't want to separate weak acids into their ions. So if you have an ionic equation involving weak acids, remember that. That's the key reason I brought it up here. All right, so that's the final net ionic equation. All right, any last questions before I let you go? All right, have a good spring break, and I'll see you in about 10 or 11 days, whatever that is.